Take a moment to settle in. Lay down comfortably, close your eyes, and allow your body to soften as you prepare to drift through the vastness of the universe. Let the quiet of the room become the backdrop for a journey that stretches across millions of light years, where distances are incomprehensible and the motions of galaxies are drawn by forces unseen. Have you ever wondered what invisible hand guides our Milky Way, nudging it imperceptibly through the dark expanse of space? What unseen presence could be tugging at the fabric of our cosmic neighborhood, drawing our galaxy and countless others toward a distant destination? It is a question that has intrigued astronomers for decades, leading them to chart the subtle motions of galaxies and, in doing so, uncover one of the most enigmatic features of the local universe, the Great Attractor. The universe is not still. Despite the apparent calm of the night sky, every galaxy is in motion, carrying its stars, dust, and dark matter along trajectories shaped by the gravitational landscape of the cosmos. The Milky Way itself drifts at an average velocity of over 600 kilometers per second relative to the cosmic microwave background, a remnant radiation field left over from the birth of the universe. This motion is not random, but guided by the gravitational pull of nearby structures, the aggregated mass of clusters, superclusters, and the subtle tug of matter too faint or dark to detect directly. Early observations revealed that galaxies did not move solely as predicted by the distribution of visible matter. Measurements of galaxy velocities, when compared to their redshifts and positions, showed deviations from uniform expansion. Some clusters of galaxies appeared to be moving toward regions of space where no luminous mass could be seen. These deviations were named peculiar velocities, and their detection marked the first clues that something immense and hidden was exerting influence across tens of millions of light years. The first hints of this mysterious influence emerged in the late 20th century, as astronomers began mapping galaxy motions in greater detail. Surveys of spiral and elliptical galaxies in the local universe indicated a consistent flow toward a region in the constellation Centaurus, lying partially obscured by the dense plain of the Milky Way. This region, later known as the Great Attractor, defied easy study. Dust, gas, and stars in the galactic plane blocked direct optical observation, concealing the full extent of the mass concentration and leaving only indirect signs of its presence. To probe this hidden territory, scientists relied on measurements of galaxy distances and velocities. Techniques such as the Tully-Fisher relation, which links the rotational speed of spiral galaxies to their intrinsic brightness, allowed astronomers to infer distances independently of redshift. By comparing these distances to the velocities derived from spectral shifts, the directional pull of the Great Attractor emerged as a coherent pattern. Galaxies were moving along a stream, collectively drawn toward a region lying approximately 150–250 million light-years from Earth. Subsequent studies using X-ray and infrared observations revealed that the Great Attractor resides within a larger network of clusters, filaments, and voids forming the cosmic web. Its mass is not concentrated in a single object, but spread across an intricate lattice of galaxy clusters, intergalactic gas, and substantial quantities of dark matter. While direct imaging is limited by obscuration, surveys in the infrared and high-energy spectra can penetrate the dust, revealing dense knots of galaxies that trace the gravitational center of this enormous structure. The estimated mass of the Great Attractor is staggering. Calculations based on the motions of surrounding galaxies suggest a mass equivalent to tens of thousands of Milky Way galaxies, exerting a gravitational pull sufficient to influence the flow of galaxies across a volume hundreds of millions of light years in diameter. The distribution of this mass, combined with the surrounding structure of the Laniakea supercluster, defines a vast basin in which our galaxy resides, gently guiding the Milky Way along a path set by the cosmic currents that sweep through the local universe. Understanding the Great Attractor is as much a matter of observation as interpretation. The obscuring zone of the Milky Way requires astronomers to integrate data across multiple wavelengths and rely on indirect traces of mass, including the motion of galaxies and the temperature and density of intergalactic gas. This synthesis of evidence paints a picture of a gravitational well whose precise contours remain elusive, yet whose influence is undeniable. It exerts a silent, continuous tug, shaping the paths of entire clusters and subtly steering the motion of our own galaxy within the Laniakea supercluster. Peering further into this hidden region requires patience and ingenuity, for the Great Attractor is cloaked behind the dense stars and interstellar material of our own galaxy. Optical telescopes, which capture visible light, are largely ineffective in penetrating this veil, so astronomers turn to instruments sensitive to infrared and X-ray wavelengths. Infrared light slips past the dust, revealing galaxies that would otherwise remain invisible, while X-ray emissions trace the hot gas permeating massive galaxy clusters, marking concentrations of mass even where individual stars cannot be resolved. Through these observations, the skeletal framework of the Great Attractor begins to emerge, an outline of immense scale shaped by both visible and unseen components. The Laniakea supercluster, of which the Great Attractor forms a central node, spans more than 500 million light-years across. Within this supercluster, galaxies and clusters follow intricate trajectories dictated by the underlying gravitational landscape. Their motions, mapped with meticulous precision, illustrate the interconnected flows that define the cosmic web. Rather than drifting randomly, galaxies trace paths that converge toward nodes of high mass concentration. The Great Attractor represents one of these nodes, its gravitational influence subtly accelerating the Milky Way and neighboring clusters along a shared vector through space. Mass estimates of the Great Attractor rely on the velocities of surrounding galaxies and the density of matter inferred from X-ray emissions. Observations suggest a gravitational pull strong enough to account for a large fraction of the peculiar velocity of our local group, guiding motion across a region stretching tens of millions of light-years. Yet even with these measurements, the exact composition remains partially hidden. Dark matter, which interacts gravitationally but emits no light, likely accounts for a substantial proportion of the total mass, silently shaping the flow of galaxies. The remaining mass consists of visible galaxy clusters and intergalactic gas, each contributing to the overall gravitational well that anchors the supercluster. Mapping these flows demands careful statistical analysis and precise distance measurements. Spiral galaxies offer one method through the Tully-Fisher relation, connecting their rotation rates to intrinsic luminosity, while elliptical galaxies rely on correlations between stellar velocity dispersion and brightness. Combining these approaches allows astronomers to build three-dimensional maps of galaxy positions and motions, revealing coherent streams converging toward the Great Attractor. The resulting flow patterns are striking in their consistency, evidence that the gravitational influence extends far beyond the immediately visible structures, encompassing hundreds of millions of light years and affecting countless galaxies. The hidden nature of the Great Attractor emphasizes the importance of multi-wavelength astronomy. Radio observations can detect neutral hydrogen gas, tracing galactic motion where light is obscured, while space-based infrared telescopes capture the faint glow of galaxies, otherwise lost in the Milky Way's glare. X-ray emissions reveal the presence of high-temperature gas, indicating deep gravitational wells and the locations of massive clusters. Each wavelength contributes a piece of the puzzle, gradually transforming what was once an invisible pull into a tangible feature of the cosmic landscape, allowing scientists to reconstruct both structure and motion with remarkable fidelity. Within this vast network, the Great Attractor does not exist in isolation. It is part of a hierarchy of structures, connected by filaments of galaxies and interspersed with immense voids. The cosmic web, visible through detailed surveys, demonstrates that matter in the universe is unevenly distributed, flowing along filaments into dense nodes. These nodes, including the Great Attractor, dominate local gravitational dynamics, shaping trajectories over scales far exceeding individual clusters. The Milky Way, along with its neighboring galaxies, is carried along one such flow, its motion a testament to the influence of structures whose presence can only be inferred through careful observation and measurement. Despite decades of study, many details about the Great Attractor remain uncertain. The obscuration by the Milky Way prevents direct imaging of its core, leaving astronomers to estimate the exact mass and precise location through indirect methods. Comparisons with surrounding superclusters, analysis of X-ray luminosity, and studies of peculiar velocities all contribute to a convergent understanding, yet the interplay between visible matter and dark matter continues to challenge comprehensive modeling. Even so, the evidence is undeniable. The Milky Way is moving, not arbitrarily, but as part of a vast, coherent motion toward a gravitational center defined by the Great Attractor, embedded within the larger structure of Laniakea. As the mapping of the Great Attractor progressed, astronomers began to observe its influence extending far beyond immediate neighbors. Galaxies within tens of millions of light years exhibited coherent motion, streaming along trajectories that hinted at a common gravitational destination. The Milky Way itself participates in this drift, accompanied by the local group of galaxies, including Andromeda and numerous smaller companions. Their collective motion toward the Great Attractor is subtle when measured against the vast scales of intergalactic space, yet it is consistent, measurable, and persistent, a gentle but inexorable tug visible only through careful calculation and observation. Beyond the immediate surroundings, the structure of Laniakea emerges as a vast basin, defined not by sharp boundaries, but by the paths traced by countless galaxies. Flow lines, mapped using velocities and distances, delineate the regions where galaxies converge toward the Great Attractor, distinguishing them from neighboring superclusters where flow patterns diverge. These convergences reveal a gravitational topography, a landscape of cosmic valleys and ridges carved by the distribution of mass, both luminous and dark. Each galaxy's movement contributes to the overall picture, painting a three-dimensional portrait of motion across hundreds of millions of light years. Within this environment, clusters such as Norma, Centaurus, and Hydra become prominent nodes, each contributing to the overall gravitational pull of the Great Attractor. Observations in X-ray wavelengths reveal vast reservoirs of hot intergalactic gas surrounding these clusters, evidence of deep potential wells that bind galaxies together. The energy emitted by this gas, measurable in millions of degrees Kelvin, traces the contours of mass otherwise invisible, allowing astronomers to infer the scale and distribution of the hidden structures. Even when stars are obscured or absent, the gravitational influence manifests through these indirect signals, offering a glimpse into the unseen framework shaping the cosmic neighborhood. Infrared surveys, particularly those capable of penetrating the dense dust of the Milky Way's plane, have identified additional galaxies contributing to the flow toward the Great Attractor. Their distribution forms elongated filaments that stretch across intergalactic space, linking clusters in a complex lattice. These filaments are not isolated. They intersect, overlap, and merge in regions of higher density, reflecting the underlying scaffolding of dark matter that directs the formation and motion of galaxies. The Great Attractor sits at the intersection of several such filaments, a central node whose gravitational dominance orchestrates the paths of neighboring galaxies along converging trajectories. The interplay between visible and dark matter becomes apparent when examining the velocities of galaxies at different distances. While luminous galaxies account for a portion of the gravitational pull, the total influence required to produce observed motions exceeds what can be explained by visible matter alone. Dark matter, undetectable through emitted light, provides the missing mass, shaping the large-scale flows and ensuring coherence across the supercluster. Its presence is inferred from the acceleration of galaxies, the temperature of intracluster gas, and the binding of massive clusters, establishing that the Great Attractor is a composite of both the familiar and the unseen, a convergence of matter that challenges direct observation but confirms its influence through effect. The scale of these motions is staggering. The local group traveling toward the Great Attractor at hundreds of kilometers per second will continue this journey over millions of years. While imperceptible on human timescales, this motion is a constant reality, a subtle drift within the gravitational basin defined by the surrounding supercluster. Every star, every nebula, every spiral arm of the Milky Way participates in this slow migration, carried along by a force that cannot be felt but is evident in the precise measurements of galactic velocities. It is a reminder of the immense scales over which gravity operates, a demonstration that the universe is dynamic, structured, and interconnected far beyond immediate perception. This flow of galaxies also reveals the hierarchical nature of cosmic structure. Small groups combine into clusters, clusters into superclusters, and superclusters into filaments and walls, each level influencing the next through gravity. The Great Attractor exemplifies this hierarchy, acting as a central node within Laniakea, which itself is part of a larger network of superclusters and voids. By studying the motions toward the Great Attractor, astronomers can trace the contours of mass across these scales, understanding not just where galaxies are, but why they move as they do, revealing the underlying geometry and mass distribution of the observable universe. To trace the full extent of the Great Attractor's influence, astronomers rely on precise measurements of distances and velocities across vast volumes of space. Surveys such as the 2-micron All-Sky Survey, 2MAS, have catalogued millions of galaxies, providing infrared data capable of piercing the Milky Way's dense disk. By combining positional information with redshift measurements, scientists can construct three-dimensional maps that reveal not only where galaxies are, but how they move relative to the cosmic expansion. These maps display the subtle curvature of flows toward the Great Attractor, illustrating the way mass concentrations bend trajectories over immense distances. X-ray observations further complement these surveys by revealing the energetic signatures of hot intra-cluster gas. In massive clusters, gas heated to tens of millions of degrees emits X-rays, indicating the depth of gravitational wells and the concentration of mass. By mapping the distribution and intensity of this radiation, astronomers can infer the presence of otherwise invisible structures, discerning clusters that are partially or entirely hidden behind the galactic plane. Each detected cluster adds a piece to the puzzle, outlining the contours of the Great Attractor and refining estimates of its total mass. The Great Attractor's role extends beyond simply drawing nearby galaxies. It participates in a network of large-scale flows, connecting to other significant structures such as the Shapley supercluster, which lies farther along the same general vector. These flows are not random. They exhibit coherence across hundreds of millions of light-years, demonstrating that gravitational influence operates on extraordinary scales. The Milky Way's journey toward the Great Attractor is a small but measurable component of a much larger migration, part of a dynamic system in which the distribution of mass defines the movement of galaxies through cosmic time. Understanding these flows requires sophisticated modeling, integrating observations with theoretical frameworks of cosmology. Numerical simulations of large-scale structure formation, incorporating both dark matter and baryonic matter, reproduce the patterns observed in the local universe. In these simulations, regions with the density and configuration of the Great Attractor naturally arise, and the predicted motions of galaxies match measured velocities, confirming the gravitational significance of these concentrations. Such models also reveal the interconnectedness of superclusters, filaments, and voids, demonstrating how the Great Attractor functions as a central node within a larger gravitational network. Beyond the technicalities of measurement, the physical composition of the Great Attractor remains a subject of close investigation. It is not a single object, but a complex assembly of galaxy clusters, groups, and intergalactic gas, all embedded within a dominant halo of dark matter. The Norma cluster, one of the densest concentrations within this region, exemplifies the interplay between luminous and invisible mass. Galaxies within Norma interact gravitationally, their motions influenced by the combined pull of nearby clusters and the overarching dark matter distribution. These interactions generate additional X-ray emission as gas is compressed and heated, providing further observational clues to the structure's mass and dynamics. The gravitational pull exerted by the Great Attractor influences the peculiar velocities of galaxies in the local universe, producing measurable deviations from the uniform expansion described by Hubble's law. These deviations, though modest relative to cosmic distances, are consistent across diverse galaxy types and locations, forming a coherent pattern that delineates the gravitational basin of Laniakea. The flow lines converge not only on the immediate region of the Great Attractor, but also toward its surrounding filaments, reflecting the broader distribution of matter and the cumulative influence of multiple mass concentrations acting in concert. Infrared and X-ray data reveal additional complexity. Filaments connecting the Great Attractor to other superclusters contain smaller groups of galaxies, themselves moving along the same general trajectory. These filaments, while less dense than the central node, contribute to the overall gravitational field, guiding galaxies along gently curved paths. By mapping these structures in detail, astronomers can trace the gradient of gravitational potential across the supercluster, understanding how mass is distributed and how it orchestrates motion on scales vastly exceeding those of individual clusters. Even with advanced instrumentation, observational challenges persist. The densest regions of the Milky Way obscure portions of the Great Attractor, and intergalactic gas can complicate X-ray measurements. Nevertheless, by synthesizing multi-wavelength data, astronomers build an increasingly coherent model of the region, confirming that it is not only a concentration of mass, but also a pivotal feature in the local flow of galaxies. Each new survey adds clarity, revealing previously hidden galaxies, refining velocity measurements, and strengthening the understanding of how the Great Attractor governs the motion of the Milky Way and its neighboring systems. Within the gravitational domain of the Great Attractor, individual galaxy clusters reveal intricate dynamics, each cluster a miniature ecosystem of stars, gas, and dark matter, bound together by gravity. The Norma cluster, situated near the central region, exemplifies this complexity. Its dense population of galaxies interacts through gravitational encounters, subtly altering trajectories and redistributing angular momentum. Hot intracluster gas, compressed and heated by these interactions, emits X-rays that trace the contours of the cluster's potential well, providing astronomers with a window into its otherwise invisible mass. Observing these emissions allows for estimates of both baryonic matter and the dark matter halo, revealing the scale of the cluster's gravitational influence. Other nearby clusters, including Centaurus and Hydra, participate in the larger flow toward the Great Attractor, their collective mass contributing to the coherent motion of galaxies throughout the region. Each cluster's mass and position subtly shape the gravitational landscape, creating paths along which smaller groups and isolated galaxies drift. These interactions occur over vast distances, yet the underlying patterns are measurable, as galaxy velocities and positions, when combined across multiple clusters, reveal consistent streams converging toward the gravitational center. This behavior illustrates that the Great Attractor's pull is not isolated, but distributed, a cumulative effect of interconnected masses shaping the trajectories of entire cosmic neighborhoods. The filaments linking these clusters form bridges of matter that guide galaxies along their paths. Within these structures, matter is concentrated yet diffuse, interspersed with voids where fewer galaxies exist. The interplay of filaments, clusters, and voids creates a dynamic network, a cosmic web through which galaxies move with directionality dictated by gravitational potential. The flow lines traced by observations demonstrate how galaxies are not randomly scattered, but directed by the invisible architecture of mass that permeates the universe, converging upon the Great Attractor as the dominant gravitational node within this region. Mapping these flows requires careful calibration of distances and velocities, with small errors potentially altering interpretations of the gravitational landscape. Astronomers utilize multiple methods, including standard candles, such as Cepheid variables and surface brightness fluctuations in elliptical galaxies, to refine distance estimates. Combining these measurements with redshift data provides three-dimensional vectors for each galaxy, revealing not just location, but motion through space relative to the cosmic microwave background. By integrating data across thousands of galaxies, the cumulative picture of motion emerges, showing how the Great Attractor directs the Milky Way and surrounding clusters along a coherent path. Observations reveal that the Milky Way's motion is not directed precisely toward a single point, but along a region defined by the aggregate mass of the Great Attractor and surrounding structures. Its trajectory is shaped by the combined gravitational pull of multiple clusters, filaments, and dark matter concentrations, creating a gently curved path rather than a straight line. This nuanced motion highlights the complexity of gravitational interactions at large scales, illustrating how the universe's structure, invisible yet tangible through its influence, governs the movement of galaxies over millions of light years. Hot gas within these clusters, often reaching tens of millions of Kelvin, continues to emit X-rays, providing a persistent signal of mass concentration. The distribution of this gas offers insight into the arrangement of dark matter, which dominates the mass budget but remains invisible to direct observation. By correlating X-ray emissions with the velocities of member galaxies, astronomers refine their understanding of how mass is distributed and how it contributes to the overarching flow toward the Great Attractor. Each new observation adds precision, revealing both the structure's extent and its role in orchestrating the motion of galaxies across the local universe. The interplay of clusters, filaments, and voids illustrates a fundamental property of cosmic structure. Gravity acts over vast scales, creating coherent patterns that guide motion. Even isolated galaxies, far from major clusters, are subtly influenced by the overall gravitational potential, their peculiar velocities reflecting the distant pull of massive concentrations. The Great Attractor, as one of the most prominent nodes in this network, exemplifies how large-scale mass distribution shapes the trajectories of galaxies, dictating motion across hundreds of millions of light years and defining the flow of the local universe with a quiet, persistent influence. Beyond the immediate clusters, the Great Attractor's influence reaches into neighboring superclusters, subtly guiding the motion of galaxies well beyond Laniakia's boundaries. The Shapley supercluster, positioned farther along the same general vector, contributes additional gravitational pull, demonstrating that these structures are interconnected, their combined masses shaping flows across the local universe. Observations indicate that galaxies within these distant regions, although separated by tens of millions of light years, exhibit velocities slightly altered by the presence of the Great Attractor, underscoring its role as a central component in a larger network of mass concentrations. Astronomers studying this region rely increasingly on multi-wavelength surveys to capture the full picture. Infrared mapping, penetrates the dust of the galactic plane, revealing hidden galaxies that optical telescopes cannot detect. X-ray instruments uncover the hot gas permeating massive clusters, while radio observations trace neutral hydrogen, outlining filaments that connect clusters across space. Each method contributes complementary data, allowing scientists to reconstruct the three-dimensional gravitational landscape with unprecedented detail. By integrating these observations, the flow patterns toward the Great Attractor become clearer, showing a coherent convergence of galaxies along multiple filaments into a central gravitational basin. Dark matter remains central to understanding these dynamics. Although it emits no light, its gravitational influence dominates the movement of galaxies within and around the Great Attractor. Simulations that incorporate dark matter reproduce observed velocities with remarkable fidelity, demonstrating that visible clusters alone cannot account for the peculiar motions measured in the local universe. The distribution of dark matter forms a scaffold upon which galaxies assemble, guiding both their positions and trajectories. In this framework, the Great Attractor is not a singular object, but an extended region of enhanced density, where dark matter and luminous matter combine to shape the paths of entire galaxy populations. The intricate web of filaments connecting clusters adds subtle complexity to the motion of individual galaxies. Galaxies do not move in isolation. Their paths are influenced by the collective gravitational field of multiple filaments, each exerting a slight curvature on trajectories. Observations reveal that even galaxies at the edges of these filaments experience measurable acceleration toward the central mass of the Great Attractor. The resulting flow lines, when visualized, resemble a network of streams converging into a central basin, each line tracing the influence of both visible clusters and the underlying dark matter scaffold. This demonstrates the layered hierarchical nature of gravitational influence, from individual clusters to superclusters and beyond. X-ray observations provide further insight into the internal dynamics of clusters feeding the Great Attractor. The gas within these clusters, heated by gravitational compression and collisions among galaxies, emits radiation that can be measured to infer mass distribution. The temperature and density of this intra-cluster medium reveal the depth of gravitational wells and highlight the regions of greatest mass concentration. Combined with velocity measurements, these data allow astronomers to model the cumulative gravitational pull exerted by the Great Attractor, confirming its capacity to direct motion across hundreds of millions of light years with subtle yet measurable precision. The flow of the Milky Way toward this gravitational center exemplifies the broader pattern observed across the local universe. The local group's motion, determined through the cosmic microwave background and redshift surveys, shows a steady drift toward the Great Attractor, shaped by the combined pull of clusters, filaments, and unseen dark matter. While the Milky Way remains unaware of its movement in a perceptible sense, its trajectory is precisely charted through meticulous observation and calculation, providing evidence of the gravitational forces at play. The path traced is not linear, but gently curved, reflecting the influence of neighboring structures and the diffuse distribution of mass across the supercluster. Filaments connecting the Great Attractor to more distant regions demonstrate the continuity of gravitational influence. These elongated structures carry galaxies along coordinated paths, their motion directed by gradients in the gravitational potential. Within these filaments, matter is less dense than in central clusters, but sufficient to guide trajectories over immense distances. Observations of these flows reveal a delicate balance. Galaxies follow the contours of the gravitational landscape, moving along paths determined by both visible mass and the invisible framework of dark matter. The resulting motion is a complex but coherent pattern, illustrating the interconnectedness of the cosmic web and the central role of the Great Attractor within it. Smaller clusters and groups within the vicinity of the Great Attractor also contribute to the overall gravitational landscape, subtly influencing the velocities of surrounding galaxies. Each aggregation of matter, while minor compared to massive nodes like Norma or Centaurus, adds nuance to the flow patterns, bending trajectories and accelerating motion in directions consistent with the central pull. Observations of these groups, often conducted in infrared to bypass the Milky Way's obscuring plane, reveal concentrations of galaxies whose combined mass reinforces the dominant gravitational signal. The interplay between major clusters and these smaller companions creates a layered structure where the movement of galaxies reflects contributions from multiple sources of gravitational influence. Detailed velocity surveys have shown that the Milky Way's motion is not only toward the Great Attractor, but also subtly affected by nearby voids and less dense regions. Areas of lower mass exert comparatively less gravitational attraction, allowing surrounding matter to drift more freely, thereby shaping the paths of galaxies into gently curved trajectories. Peculiar velocities measured across different regions indicate that the gravitational pull is distributed over an extensive volume, rather than concentrated at a single point, emphasizing the diffuse and composite nature of the Great Attractor as an extended mass concentration embedded within the cosmic web. Measurements of cluster mass within the Great Attractor region are refined through a combination of techniques. X-ray luminosity provides insight into the density and temperature of intracluster gas, while the motions of individual galaxies within clusters inform estimates of gravitational potential. Observations of galaxy mergers and interactions reveal how energy and momentum are redistributed, offering additional constraints on mass distribution. These analyses consistently indicate that dark matter constitutes the majority of the total mass, silently governing motion across the region and ensuring the coherent flow of galaxies toward the gravitational center. The structure of filaments linking clusters demonstrates the guiding influence of gravitational gradients on smaller scale flows. Galaxies within these filaments are funneled along elongated paths, their velocities gradually aligning with the general direction of convergence. While individual galaxies may experience local perturbations due to interactions with neighbors or tidal forces from nearby clusters, the overarching pattern remains clear. Matter is drawn toward the Great Attractor along preferred pathways, illustrating the cumulative effect of multiple gravitational sources operating across intergalactic space. Infrared surveys continue to reveal previously hidden galaxies behind the dense plane of the Milky Way, filling in gaps in our understanding of the region's structure. Each newly catalogued galaxy adds precision to flow maps, allowing astronomers to trace subtle deviations in trajectories and refine models of the underlying mass distribution. X-ray data confirm the presence of additional clusters their hot gas revealing gravitational wells that contribute to the total pull experienced by the Milky Way and surrounding galaxies. By combining data across wavelengths, a more complete picture emerges, one in which both luminous and dark matter work together to define the flow toward the Great Attractor. Numerical simulations of large-scale structure provide a complementary perspective, demonstrating how the observed distribution of galaxies and clusters naturally arises from gravitational interactions. These models incorporate both dark matter and baryonic matter, reproducing the velocity patterns measured in the local universe with remarkable accuracy. In simulated universes, regions with characteristics similar to the Great Attractor appear consistently as nodes at the intersections of multiple filaments, confirming that such structures are an expected outcome of cosmic evolution. Observations and simulations together affirm the central role of the Great Attractor in directing the motion of the Milky Way and its neighbors. The cumulative effect of these multiple influences, clusters, groups, filaments, and dark matter, creates a coherent flow that extends across hundreds of millions of light-years. Galaxies within this region move with velocities that, while modest relative to cosmic scales, are consistent, predictable, and measurable. Each contributes to the larger pattern, tracing the contours of gravitational potential defined by the combined mass of visible and invisible matter. The Milky Way's journey toward the Great Attractor is part of this vast, interwoven motion, its trajectory shaped by both local and distant influences within the cosmic web, reflecting the universe's underlying architecture. Over the decades, progressively refined observations have allowed astronomers to map the Great Attractor with increasing precision. Early surveys hinted at its existence through peculiar velocities, but modern instruments, spanning infrared, X-ray, and radio wavelengths, reveal an intricate tapestry of clusters, filaments, and intergalactic gas. Each dataset contributes a layer of detail, filling gaps created by the obscuring plane of the Milky Way and providing cross-verification for the measurements of galaxy motion. Through careful calibration and repeated observation, the gravitational landscape becomes increasingly well-defined, showing how mass concentrations, both luminous and dark, converge to guide the motion of galaxies across vast distances. Adjacent superclusters also interact with the Great Attractor, creating subtle perturbations in the flow of galaxies. While Laniakea channels matter toward the central node, neighboring superclusters exert their own pull, gently curving the paths of galaxies as they move along filaments. The interplay between these massive structures is observable through velocity surveys, where deviations from linear trajectories reveal the presence of competing gravitational influences. Each galaxy's motion is thus the sum of multiple forces, yet the overarching convergence toward the Great Attractor remains unmistakable, indicating its dominant role within this region of the universe. Velocity measurements continue to refine our understanding of mass distribution. Redshift data, when combined with distance indicators such as Cepheid variables and surface brightness fluctuations, allow for the construction of three-dimensional flow maps. These maps illustrate the gradient of gravitational potential across the supercluster, showing not only where galaxies are moving, but how strongly they are influenced by the cumulative mass. Subtle variations in velocity indicate areas of higher or lower density, revealing the uneven distribution of matter and highlighting the intricate structure of the Great Attractor's gravitational basin. The complex interplay of dark matter and visible structures becomes evident when comparing observed flows with theoretical models. Simulations that incorporate dark matter halos reproduce the observed velocity patterns with remarkable accuracy, confirming that unseen mass dominates the dynamics of the region. Luminous clusters such as Norma and Centaurus provide measurable signals, but without the gravitational contribution of dark matter, the peculiar velocities of the Milky Way and neighboring galaxies would be significantly lower. The alignment between observational data and simulations strengthens the conclusion that the Great Attractor is a composite of both visible and invisible matter, forming an extended region of enhanced density that governs the motion of galaxies across hundreds of millions of light-years. Filamentary structures continue to channel galaxies along defined paths, creating coherent streams that converge upon the gravitational center. These filaments, though less dense than central clusters, maintain sufficient mass to guide the movement of smaller groups and isolated galaxies. Observations of galaxy motion within these elongated structures demonstrate gradual acceleration toward the Great Attractor, providing further evidence of the extended reach of its gravitational influence. In regions where filaments intersect, the convergence becomes particularly pronounced, illustrating the hierarchical nature of mass distribution and the coordinated flow of matter within the cosmic web. The local group's trajectory offers a measurable example of these dynamics. Traveling at hundreds of kilometers per second, the Milky Way and its neighboring galaxies move as part of this larger convergence, their paths gently bending under the influence of both nearby clusters and distant filaments. Though imperceptible to human senses, this motion is precisely determined through observation of cosmic microwave background anisotropies, redshift surveys, and peculiar velocity studies. The consistency of the local group's motion with models of the Great Attractor's gravitational pull reinforces the accuracy of large-scale mapping and confirms the profound influence of this hidden concentration of mass. Cumulative observations across wavelengths, combined with numerical modeling, reveal the vast scale of the Great Attractor's effect. Each galaxy, cluster, and filament participates in a coordinated pattern, tracing gradients of gravitational potential that extend across hundreds of millions of light-years. The coherent convergence observed throughout Laniakea and neighboring structures demonstrates that motion on these scales is not chaotic, but highly ordered, dictated by the distribution of mass and the interconnection of cosmic structures. In this way, the Great Attractor emerges as a central organizing feature, its invisible hand subtly directing the movement of the Milky Way and countless other galaxies within the local universe. The study of cosmic voids further illuminates the gravitational context surrounding the Great Attractor. These vast regions, comparatively empty of galaxies, provide contrast to the dense nodes and filaments that dominate the local universe. Galaxies at the edges of voids experience weaker gravitational pull from the sparse surroundings, allowing the dominant influence of nearby massive structures to shape their motion more clearly. Observations indicate that the Milky Way's trajectory is not merely a response to mass in the immediate vicinity, but also a reflection of the differential forces between dense clusters and the surrounding low-density regions. The juxtaposition of voids and filaments accentuates the directionality of flows, revealing pathways along which matter streams toward concentrated regions like the Great Attractor. Mapping these voids and filaments requires extensive surveys capable of capturing both the brightest and faintest galaxies across the sky. Infrared and radio wavelengths play a crucial role in detecting galaxies hidden behind the Milky Way, while deep optical surveys reach into the more transparent regions of space, cataloging galaxies across large distances. By compiling these observations, astronomers construct detailed three-dimensional models that display not only the positions of galaxies, but the velocities along their trajectories. The resulting maps portray the Great Attractor as the focal point of converging flows, a gravitational sink toward which matter streams from surrounding voids and filaments alike. Within the filaments, galaxies do not move uniformly, but exhibit subtle variations in speed and direction, influenced by local density and nearby clusters. These variations provide additional insight into the distribution of mass within the Great Attractor region. Galaxies moving faster along certain streams suggest areas of higher gravitational potential, while slower motion along less dense paths reflects weaker pull. By analyzing these differences, astronomers can infer the gradient of the gravitational field, estimating both the concentration and spread of mass, and refining the understanding of how the Great Attractor orchestrates motion on scales far exceeding those of individual clusters. The behavior of galaxy groups within filaments further demonstrates the cumulative effect of gravitational interactions. Small clusters follow the paths defined by larger neighboring nodes, their motion guided not only by the nearest massive cluster, but by the aggregate influence of surrounding filaments and distant superclusters. This hierarchy of attraction ensures a coherent flow across hundreds of millions of light years, where each galaxy, each group, responds to a combination of forces, yet ultimately participates in the overall convergence toward the Great Attractor. The resulting pattern is both intricate and ordered, a natural outcome of gravity acting over immense scales. Observational refinement continues with studies of the temperature, density, and motion of intracluster gas. X-ray measurements trace the hot plasma permeating massive clusters, revealing the depth of gravitational wells and providing indirect evidence of the dark matter content. By combining these data with galaxy velocity measurements, astronomers gain a comprehensive view of mass distribution within the region. Each cluster, each filament, contributes to the cumulative pull, shaping the coherent motion of galaxies, including the local group, which drifts steadily toward the center of the gravitational basin defined by the Great Attractor. The influence of the Great Attractor extends even to galaxies on the periphery of Laniakea, where the combined gravitational effects of multiple clusters and filaments converge. Observations indicate that while the dominant direction of flow aligns with the central mass, local deviations occur due to nearby structures and underdense regions. These subtle variations, measurable only through precise velocity mapping, demonstrate the complexity of large-scale flows and the intricate interplay between gravitational forces on multiple scales. Even at these distances, the Great Attractor asserts a measurable influence, guiding matter along preferred pathways within the cosmic web. Numerical simulations of these flows, incorporating both baryonic and dark matter, reproduce the observed patterns with remarkable fidelity. Simulated galaxies follow paths that mirror the converging trajectories measured through surveys, confirming that the Great Attractor functions as a gravitational focal point within a network of interconnected superclusters and filaments. These simulations also highlight the scale over which its influence operates, demonstrating that the Milky Way and its neighboring galaxies are part of a broader movement dictated by the distribution of mass across hundreds of millions of light-years, an ongoing journey shaped by forces both visible and invisible. Observations over the last several decades have steadily refined our understanding of the local group's trajectory within this intricate gravitational landscape. By combining redshift data, measurements of peculiar velocities, and the cosmic microwave background frame of reference, astronomers have mapped the Milky Way's motion with exceptional precision. The flow is not directed toward a single point, but instead follows a broad basin of attraction defined by the cumulative mass of clusters, filaments, and intergalactic gas within the Great Attractor region. Each galaxy in the local group contributes subtly to this motion, and the aggregate movement exemplifies the collective influence of a large-scale gravitational field that extends well beyond individual clusters. Comparisons with other prominent mass concentrations in the nearby universe provide additional perspective. While the Shapley supercluster exerts measurable pull along a similar vector, its influence is secondary to the central mass of the Great Attractor, which dominates the local flow. The interplay between these gravitational centers creates nuanced trajectories for galaxies, their paths bending subtly under the combined forces. Even regions that appear sparsely populated exhibit small but measurable deviations in motion, reflecting the distant influence of massive structures and confirming that the universe's architecture is interconnected across immense scales. The dynamics of dark matter within the Great Attractor region are central to understanding these patterns. While luminous clusters and galaxies provide visible markers, dark matter constitutes the majority of the mass-shaping flows. Its distribution forms a continuous halo encompassing clusters and filaments, generating the gravitational gradients that guide galaxy motion. Observational inferences, supported by numerical simulations, suggest that the dark matter halo extends far beyond the luminous regions, subtly influencing trajectories across the supercluster. The alignment between predicted and observed motions reinforces the conclusion that dark matter governs large-scale flows, orchestrating the movement of the local group and neighboring galaxies alike. Refined velocity maps reveal coherent streams within the region, tracing the paths along which galaxies converge toward the gravitational center. These streams illustrate the combined effect of multiple mass concentrations, each contributing to the overall pattern. Galaxies in smaller groups follow trajectories molded not only by immediate clusters, but also by distant filaments and nodes, creating a hierarchical system of motion. The integration of these multiple influences produces a flow that, while complex in detail, remains consistently directed toward the Great Attractor, highlighting its central role within the local cosmic web. X-ray and infrared observations continue to identify hidden structures, filling in gaps left by the Milky Way's obscuring plane. Hot gas detected in X-rays delineates the depths of gravitational wells within clusters, while infrared surveys reveal galaxies previously invisible in optical wavelengths. Together, these observations provide a comprehensive map of mass distribution, enabling precise estimates of the gravitational forces at play. By cross-referencing data across wavelengths, astronomers refine models of the Great Attractor, revealing the interplay between visible matter, dark matter, and the large-scale flow patterns that define the motion of the Milky Way and surrounding galaxies. The local group's trajectory, measured at hundreds of kilometers per second, is the result of this cumulative influence. While the velocity is modest relative to cosmic scales, its persistence across millions of years demonstrates the enduring effect of gravitational attraction. Each star, each planetary system, and each galaxy within the local group participates in this slow, steady drift toward the central mass concentration. A subtle but measurable journey dictated by the distribution of matter in the surrounding supercluster. Observations indicate that this motion will continue for eons, gradually reshaping the relative positions of galaxies within Laniakea as they respond to the unseen scaffolding of the universe. Numerical simulations provide further insight into the interplay between clusters, filaments, and voids. By modeling both baryonic and dark matter, these simulations reproduce the converging flow patterns observed in surveys, confirming that the Great Attractor functions as a gravitational focal point within a broader cosmic network. Simulated galaxies follow trajectories consistent with measured velocities, demonstrating how interconnected mass concentrations collectively shape motion across hundreds of millions of light years. The alignment between observation and simulation underscores the predictive power of gravitational models and highlights the central importance of the Great Attractor within the local universe's dynamic framework. Within individual clusters, feeding the Great Attractor, the internal dynamics reveal intricate patterns of motion and interaction. Galaxies orbit cluster centers in complex trajectories, influenced by both the overall gravitational potential and the localized pull of nearby companions. Collisions and close encounters, though infrequent on human timescales, redistribute momentum and energy within the system, subtly altering the velocity vectors of participating galaxies. These interactions heat intracluster gas, raising its temperature to tens of millions of degrees and generating X-ray emissions that trace the cluster's gravitational structure. Observations of this hot plasma provide direct insight into the distribution of both visible and dark matter, highlighting the interplay that shapes flows toward the central node. The intracluster medium is not static. Turbulence arises from galaxy motions, mergers, and infalling matter along filaments, creating variations in temperature and density. These variations, detectable through high-resolution X-ray spectroscopy, reveal substructures within clusters and indicate areas of enhanced mass concentration. By studying these signatures, astronomers can refine models of cluster mass and understand how localized interactions contribute to the broader gravitational influence of the Great Attractor. Even small shifts in the intracluster medium reflect the cumulative effect of motions within the supercluster, demonstrating how localized dynamics resonate through the larger cosmic flow. Filamentary connections between clusters further modulate the trajectories of galaxies. As matter streams along these filaments, it encounters varying gravitational potentials, resulting in subtle accelerations or decelerations depending on the local density and proximity to massive nodes. These gentle variations accumulate over millions of light years, producing coherent flows that converge toward the central mass of the Great Attractor. Observations of these motions, particularly in regions where filaments intersect or curve, provide evidence of the layered structure of gravitational influence, where the combined effect of multiple sources dictates the paths of galaxies within the supercluster. Dark matter continues to play a central role in these dynamics. While luminous galaxies and clusters provide visible markers, the majority of gravitational influence arises from an invisible halo extending across clusters and filaments. Its presence is inferred from galaxy motions, the binding of clusters, and the temperature of the intracluster medium. By modeling the distribution of dark matter, astronomers can reproduce the observed velocities and flows, demonstrating that the large-scale convergence toward the Great Attractor is a natural outcome of the underlying mass distribution. This unseen framework governs both the trajectories of individual galaxies and the overall coherence of flows within Laniakea. The local group's journey illustrates the cumulative effect of these layered forces. While dominated by the gravitational pull of the Great Attractor, its path is subtly shaped by interactions with nearby clusters and the filamentary network that connects them. Each galaxy in the local group responds individually to the surrounding gravitational landscape, yet collectively they move as a coherent unit along a trajectory shaped by both near and distant mass concentrations. The persistence of this motion across millions of years underscores the enduring influence of the Great Attractor, a hidden force guiding matter through the vast expanses of intergalactic space. Advancements in observational technology continue to refine our understanding of these processes. Higher resolution infrared imaging, improved X-ray detectors, and enhanced radio mapping allow astronomers to detect smaller structures and more precisely measure galaxy velocities. These improvements fill gaps in the map of the Great Attractor, revealing faint clusters, minor filaments, and subtle variations in intracluster gas. Each new detection contributes to a more complete understanding of the supercluster's structure and gravitational influence, allowing scientists to trace the paths of galaxies with increasing accuracy and revealing the intricate mechanisms by which the universe organizes itself on the larger scales. Ultimately, the interplay of clusters, filaments, intracluster gas, and dark matter produces a cohesive gravitational environment that directs the motion of galaxies across vast distances. The Milky Way, moving in concert with the local group, is carried along this intricate network, its path a measurable expression of forces that operate unseen yet with profound effect. Observations and models converge to show that the Great Attractor, though hidden and diffuse, is the focal point of a dynamic system, orchestrating flows through a combination of mass, motion, and gravitational connectivity that defines the local universe in both structure and movement. The distribution of mass across Laniakea further clarifies the scope of the Great Attractor's influence. Dense clusters, interconnected filaments, and interspersed voids create a complex, three-dimensional gravitational landscape. Regions of high density exert strong pull, drawing nearby galaxies along predictable paths, while voids provide comparatively little resistance, allowing matter to accelerate toward mass concentrations. The contrast between these extremes emphasizes the directional nature of cosmic flows. where even small variations in density contribute to the curvature and velocity of a galaxy's trajectory. Mapping these variations requires precision, combining distance measurements, redshift data, and multi-wavelength imaging to reconstruct the full gravitational topology. Surrounding voids subtly enhance the convergence of matter toward the Great Attractor. Galaxies positioned near underdense regions experience reduced gravitational opposition, effectively channeling their motion along filaments that lead into the supercluster. These voids, though seemingly empty, define boundaries that constrain flows, shaping the broader pattern of motion across the local universe. Observations indicate that the Milky Way's path is influenced not only by the pull of massive clusters, but also by the relative paucity of matter in surrounding regions, which allows the cumulative gravitational pull of the Great Attractor and neighboring structures to dominate its trajectory. The alignment of clusters, filaments, and voids produces a hierarchical system of gravitational influence. Within this system, local interactions, collisions, tidal forces, and intra-cluster gas dynamics operate on smaller scales, yet contribute incrementally to the larger motion of galaxies. Over millions of light years, the aggregation of these influences forms coherent flows, demonstrating that large-scale structure emerges from the accumulation of small, localized effects. High-resolution surveys of galaxy velocities, when integrated across the supercluster, reveal the continuous gradient of gravitational potential, tracing paths that converge toward the central mass of the Great Attractor. Infrared and X-ray observations continue to refine the three-dimensional model of mass distribution. Hidden galaxies behind the Milky Way, previously inaccessible to optical telescopes, are now catalogued with precision, filling in gaps that once obscured our understanding. The X-ray emission from hot intracluster gas delineates gravitational wells, providing a direct proxy for both visible and dark matter. By synthesizing these data, astronomers create increasingly accurate flow maps, illustrating how matter moves along filaments, through clusters, and across underdense regions in response to the cumulative pull of the Great Attractor. The extended halo of dark matter enveloping clusters and filaments reinforces these flows. Its presence, inferred from the velocities of galaxies and the binding of intracluster gas, establishes a continuous gravitational network that guides matter across vast distances. Observed trajectories align closely with models that include dark matter, confirming its central role in shaping motion. Without this unseen mass, the coherent convergence toward the Great Attractor would not occur. Galaxies would display more randomized velocities, lacking the directional drift that defines the local universe. The synergy of luminous and dark matter orchestrates a precise gravitational environment, one in which each galaxy's motion is both influenced by nearby structures and integrated into the larger supercluster flow. The local group's ongoing journey reflects the cumulative influence of these forces. As it moves through Laniakea, its path subtly bends in response to nearby clusters, filaments, and the gravitational vacuum of surrounding voids. While the motion is imperceptible on human timescales, precise measurement confirms a consistent direction and velocity toward the central mass of the Great Attractor. Every star and planetary system within the local group is carried along this trajectory, tracing a path shaped by the interplay of visible clusters, hidden dark matter, and the structural voids that define the supercluster's contours. Simulations of these large-scale flows reinforce observational conclusions, demonstrating that the convergence toward the Great Attractor arises naturally from the distribution of matter. Virtual galaxies within modeled superclusters follow trajectories remarkably similar to those observed, validating the gravitational framework that governs motion across the local universe. These simulations reveal the scale and coherence of influence, showing how clusters, filaments, and voids interact to produce a directed flow that spans hundreds of millions of light years. The Great Attractor emerges as a central gravitational focal point, its hidden mass orchestrating the ongoing motion of galaxies and shaping the structure of the surrounding cosmic web. Within the filaments connecting major clusters, individual galaxies reveal subtle variations in motion that reflect the intricate gravitational environment. Their velocities are not uniform. Slight differences arise from local density fluctuations, tidal interactions with neighboring galaxies, and the gradients of gravitational potential along the filament. These small deviations, when measured across large samples, form coherent patterns that indicate a net movement toward the Great Attractor. Even solitary galaxies, far from dense clusters, follow trajectories influenced by the combined pull of multiple structures, demonstrating the far-reaching effect of mass distributed along the supercluster's network. The convergence of filaments into central nodes accentuates the complexity of cluster interactions. As streams of galaxies flow along intersecting paths, the overlapping gravitational influences subtly redirect motion, leading to gentle curvatures and accelerations within the flow. Observations of such convergence zones show enhanced densities, with both luminous and dark matter concentrated along the intersections. These regions act as gravitational funnels, drawing matter from surrounding filaments and reinforcing the central pull of the Great Attractor. The cumulative effect ensures that even distant galaxies contribute to and follow the overarching flow toward the central mass. Intracluster dynamics within these nodes continue to evolve as galaxies interact, merge, and pass close to one another. Each encounter redistributes momentum and angular momentum, slightly adjusting the velocities of participating galaxies. The resulting patterns, observable through high-resolution spectroscopy and imaging, provide indirect measurements of the gravitational potential and mass distribution within clusters. Hot gas, compressed and heated by these interactions, emits X-rays that illuminate otherwise invisible structures, revealing the shape and depth of gravitational wells. These observations, combined with simulations, demonstrate how localized processes feed into the larger-scale convergence toward the Great Attractor. Dark matter halos envelop both clusters and filaments, creating a continuous gravitational framework that guides the motion of galaxies across vast distances. While individual clusters provide focal points for local flows, the surrounding dark matter ensures that trajectories remain coherent across the supercluster. Simulated and observed velocities align closely, confirming that dark matter's influence is essential for the maintenance of organized motion. The interplay of visible and invisible mass forms a layered system in which galaxies follow pathways shaped by both immediate interactions and long-range gravitational gradients. The local group remains embedded within this intricate network, its movement a composite of multiple influences. While the Great Attractor exerts dominant pull, neighboring clusters, intersecting filaments, and surrounding voids all contribute to the subtle curvature and velocity of its path. Observational data demonstrate that this motion is consistent with models derived from the distribution of mass throughout Laniakea, reinforcing the understanding that galaxy trajectories are not isolated phenomena, but components of a larger, interconnected flow. Each star, each galaxy within the local group participates in a movement dictated by the invisible architecture of the universe. The continued refinement of observational techniques further clarifies these patterns. Surveys utilizing infrared, X-ray, and radio wavelengths uncover previously hidden galaxies, identify faint filaments, and reveal substructures within clusters. Measurements of intracluster gas properties combined with galaxy velocities allow for precise estimation of both visible and dark matter. As these data accumulate, the models of the Great Attractor's influence become increasingly detailed, showing how individual and collective motions are guided by the extended gravitational basin. The result is a continuously evolving map of the local universe, where the flow of galaxies toward the Great Attractor is measured, understood, and quantified. In sum, the complex interplay of filaments, clusters, voids, intracluster dynamics, and dark matter constructs a vast gravitational network. Through this network, galaxies move with coherent trajectories shaped by multiple scales of influence, all converging toward the central mass concentration identified as the Great Attractor. The local group's journey, mapped with precision and confirmed by simulation, exemplifies this interaction, demonstrating how hidden forces orchestrate the motion of countless galaxies and define the structure of the nearby cosmos. Every observation, every measurement, contributes to a more complete understanding of the mechanisms driving these grand, silent flows. Over cosmological timescales, the flow of galaxies toward the Great Attractor shapes the evolution of clusters and filaments. As galaxies drift along converging paths, they occasionally merge or pass closely enough to exchange momentum, gradually altering the mass distribution within clusters. These interactions concentrate matter toward the gravitational center, deepening the potential wells and enhancing the pull on neighboring galaxies. Over millions of years, the cumulative effect reinforces the coherence of large-scale motion, gradually sculpting the supercluster's architecture into an interconnected network of dense nodes, elongated filaments, and surrounding voids. Accretion along filaments continues to feed mass into clusters, sustaining their growth and maintaining the flow toward the Great Attractor. Galaxies and groups moving along these structures contribute both baryonic matter and dark matter, reinforcing the gravitational gradients that guide subsequent trajectories. The interplay of incoming matter with the existing mass of clusters affects both velocity and trajectory, producing subtle but measurable variations in motion. By observing these patterns across many clusters, astronomers gain insight into the mechanisms by which superclusters evolve and maintain coherent flows over extended distances and timescales. Intracluster processes, such as the heating of gas and redistribution of momentum through interactions, further modify the local gravitational environment. As galaxies merge or orbit cluster centers, energy is transferred to the intracluster medium, raising its temperature and increasing pressure. The resulting hot plasma emits X-rays, revealing dense regions that coincide with with dark matter concentrations. These observations provide a window into the ongoing structural evolution of clusters, demonstrating how localized processes integrate into the broader flow toward the Great Attractor and contribute to the shaping of the surrounding supercluster. The hierarchical nature of gravitational influence ensures that flows remain organized even across vast scales. While individual clusters dominate local motion, the overarching field defined by the extended distribution of dark and visible matter maintains coherence across filaments and voids. Galaxies in smaller groups or along peripheral filaments adjust their trajectories according to the combined pull of nearby nodes, the orientation of connecting filaments, and the relative emptiness of surrounding voids. This multi-scale interaction results in smooth, directed flows that persist across hundreds of millions of light years, reflecting both local and long-range gravitational effects. Dark matter continues to underpin the structural evolution of the supercluster. Its presence extends beyond clusters, enveloping filaments and guiding the motion of infalling galaxies. Simulations that incorporate both baryonic and dark matter reproduce observed trajectories with remarkable fidelity, confirming that the continuous gravitational framework is essential for maintaining coherent flows. Without this invisible scaffold, the organized convergence toward the Great Attractor would be disrupted, leading to scattered, less predictable motions. Instead, galaxies follow pathways dictated by the integrated gravitational landscape, illustrating the profound influence of unseen mass on the architecture of the local universe. The local group remains a participant in these long-term dynamics. As it moves along the cumulative flow toward the Great Attractor, its trajectory is subtly influenced by the redistribution of mass within clusters and along filaments. Even modest interactions within the supercluster, such as the infall of a small group or the merger of neighboring galaxies, can incrementally alter the gravitational field, adjusting the local group's motion over cosmological timescales. These changes, while imperceptible in human terms, exemplify the continuous, interconnected evolution of matter within the Laniakea supercluster and the pervasive influence of the Great Attractor on local cosmic architecture. Finally, the synthesis of observational data and simulation provides a detailed picture of the dynamic equilibrium maintained within the supercluster. Filaments continue to funnel galaxies toward dense nodes, voids define the boundaries of flows, and clusters evolve through mergers and accretion, all under the guidance of the pervasive dark matter framework. The Great Attractor stands as the central gravitational anchor, coordinating these motions and maintaining the coherence of the system. Through careful measurement, modeling, and analysis, astronomers have revealed the mechanisms by which the universe organizes itself on the largest scales, showing how hidden forces govern the persistent, silent movement of galaxies across space and time. Observational techniques have become increasingly sophisticated in capturing the motions of galaxies influenced by the Great Attractor. High-resolution spectroscopic surveys allow precise measurement of redshifts, revealing the velocity components of galaxies relative to the cosmic microwave background. Combined with distance indicators such as Cepheid variables and surface brightness fluctuations, these measurements construct a three-dimensional view of motion within the Laniakea supercluster. Each galaxy's trajectory, however subtle, contributes to mapping the overall flow. revealing the directionality and magnitude of acceleration induced by both visible clusters and the pervasive halo of dark matter. Complementing direct observation, computational modeling plays a crucial role in interpreting these motions. N-body simulations, incorporating millions of particles representing baryonic and dark matter, reproduce the complex interactions between clusters, filaments, and voids. By adjusting initial conditions and mass distributions, simulations replicate the observed peculiar velocities of galaxies, confirming the central role of the Great Attractor. They also predict how small perturbations in local mass concentrations can slightly alter trajectories, demonstrating the sensitivity of galaxy motion to the integrated gravitational environment. These models bridge the gap between observation and theory, providing a framework for understanding how localized interactions cascade into large-scale coherent flows. Mass estimates are continuously refined through multi-wavelength observation. X-ray measurements of intra-cluster gas quantify the depth of gravitational wells, while gravitational lensing studies reveal distortions of background light caused by dark matter concentrations. Infrared surveys uncover galaxies obscured by the plane of the Milky Way, filling gaps in the map of mass distribution. Each technique contributes a piece of the puzzle, providing complementary evidence of the distribution of matter that guides cosmic motion. When combined, these approaches yield an increasingly precise picture of the gravitational forces directing galaxies, allowing astronomers to trace the subtle pull of the Great Attractor across hundreds of millions of light-years. The interaction of the Great Attractor with the broader cosmic environment also shapes trajectories beyond Laniakea. Adjacent superclusters, including the Shapley and Hydra Centaurus complexes, exert additional forces, gently modifying the direction of inflowing galaxies. While these influences are weaker than the central pull of the Great Attractor, they introduce measurable curvature in galaxy paths, demonstrating the interconnectedness of massive structures across the local universe. Even voids on the periphery, by providing regions of low resistance, subtly amplify the net convergence toward the central node. Together, these elements create a nuanced, multi-scale gravitational field that dictates the motion of galaxies on both local and intermediate scales. The local group's path exemplifies this interplay. Its velocity vector reflects the integrated effect of multiple clusters, filaments, and voids converging toward the Great Attractor, yet adjusted slightly by surrounding structures. The combined mass of these components shapes not only the direction, but the rate of movement, establishing a steady, coherent drift through space. While individual galaxies within the local group follow slightly different internal motions, their collective trajectory mirrors the flow of the larger supercluster, demonstrating how local systems are nested within broader cosmic patterns. This hierarchical alignment underscores the principle that large-scale gravitational forces govern both group-scale dynamics and the motion of solitary galaxies. Continuous monitoring and refinement reveal subtle changes over time as new galaxies are discovered and existing mass estimates are adjusted. The precise distribution of dark matter inferred through its gravitational effects is critical in maintaining coherence across these flows. By integrating observational data with simulations, astronomers can project trajectories far into the future, anticipating how the continued convergence of matter toward the Great Attractor will will shape the spatial organization of the local universe. Each incremental improvement in measurement enhances the resolution of this cosmic map, illustrating the persistent influence of a hidden, yet profoundly consequential, gravitational center. Within clusters themselves, the transfer of energy and momentum subtly reshapes the gravitational landscape. Galaxies orbiting cluster centers induce tidal forces that redistribute mass, gradually altering local velocity fields. Collisions, while infrequent, inject kinetic energy into the intracluster medium, generating turbulence and shocks that propagate through the hot plasma. This motion of gas, observable in X-ray and radio wavelengths, reflects the ongoing reconfiguration of gravitational potential wells, providing a dynamic record of mass interactions that contributes incrementally to the broader flow toward the Great Attractor. The intracluster gas evolves over time, cooling in some regions and heating in others, a process driven by the balance of radiative emission and energy input from galaxy motions and mergers. Denser areas retain higher temperatures due to stronger gravitational binding, while lower density regions experience gradual expansion and dissipation. These variations influence the overall pressure gradients within clusters, subtly affecting the motion of galaxies embedded in the medium. Through careful observation of temperature maps, density profiles, and X-ray emission lines, astronomers can infer the distribution of both visible and dark matter, revealing how local processes integrate with large-scale gravitational forces. As clusters accrete matter along connecting filaments, their mass increases, deepening gravitational wells and enhancing their influence on surrounding galaxies. The interaction between inflowing matter and existing cluster structure produces measurable effects, including slight acceleration of galaxies and compression of intracluster gas. Over millions of years, these processes reinforce the convergent flows directed toward the Great Attractor, maintaining the coherence observed across the supercluster. The cumulative effect of these interactions ensures that the overall motion of galaxies remains directed, even as individual orbits within clusters experience subtle variations. The architecture of Laniakea emerges from this combination of localized dynamics and large-scale gravitational gradients. Filaments serve as channels along which matter travels, connecting clusters and funneling galaxies toward the central mass. Void regions provide low-resistance pathways, allowing matter to accelerate toward denser areas. The integration of these structures forms a complex but ordered network where individual galaxies, groups, and clusters follow paths dictated by both immediate interactions and long-range gravitational influence. Observations of galaxy motion within this framework reveal the intricate balance between local perturbations and the overarching pull of the Great Attractor. Even at the periphery of the supercluster, the influence of the Great Attractor persists. Galaxies in distant filaments adjust their trajectories in response to the combined pull of clusters and the guiding structure of dark matter halos. Their motion may be subtle, yet over millions of light years, these small accelerations accumulate, aligning galaxies along coherent streams that converge on the central mass. The persistence of these flows across such distances demonstrates the remarkable reach of the gravitational influence, uniting structures separated by hundreds of millions of light years into a continuous, organized system. Ultimately, the interplay of energy transfer, intracluster gas dynamics, filamentary accretion, and dark matter scaffolding, orchestrates the steady convergence of matter. The Milky Way and the local group drift along these pathways, part of a broader, interconnected motion that reflects both local interactions and the cumulative gravitational pull of the Great Attractor. Each observational measurement, each simulation, and each refinement in mapping deepens our understanding of this hidden force, revealing the mechanisms by which the universe organizes itself on scales far beyond individual galaxies. The flow continues, imperceptible yet persistent, a silent testament to the invisible structures that govern cosmic motion. As the interplay of galaxies, clusters, filaments, and voids unfolds over vast distances, the Great Attractor emerges as the unifying presence shaping the motion of matter within Laniakea. Its gravitational influence, though invisible to the eye, is manifest in the precise trajectories of countless galaxies, each responding to the sum of forces imposed by neighboring structures and the encompassing dark matter halo. The local group, drifting steadily toward this central mass, exemplifies the measurable effect of a hidden yet pervasive gravitational field, a motion maintained consistently over millions of years. Observations confirm that even minor variations in density or mass along filaments contribute incrementally, guiding galaxies along paths that align with the overarching convergence. The coherence of these flows is a testament to the layered hierarchy of cosmic structure. Within clusters, orbital interactions and mergers subtly redistribute momentum. Along filaments, inflows of matter maintain directional consistency. Across voids, the relative absence of mass allows acceleration toward denser regions. Each of these processes, operating on different scales, integrates into a continuous system of motion. The combined effect of these influences produces a remarkable order within the apparent chaos of the universe, demonstrating that gravity, though invisible, orchestrates the silent dance of galaxies across hundreds of millions of light years. Dark matter remains central to this orchestration, its extended halos enveloping clusters and filaments, establishing gravitational gradients that persist across the supercluster. Its presence ensures that even the most isolated galaxies follow predictable paths, and that the overall flow toward the Great Attractor remains coherent. Simulations incorporating both visible and dark matter reproduce these patterns with striking accuracy, validating observational inferences and confirming the fundamental role of unseen mass in shaping the motion of the local universe. The alignment between model predictions and measured trajectories underscores the universality of gravitational principles in governing cosmic structure. The local group's gradual motion, while imperceptible in human terms, is a continuous journey guided by these layered gravitational influences. Each galaxy within the group contributes subtly to the collective velocity, yet the entire system responds as a unified entity to the central pull of the Great Attractor. The Milky Way's drift through space is thus not isolated, but an expression of a larger, integrated flow that extends across the supercluster, threading together clusters, filaments, and voids into a cohesive, measurable motion. This silent convergence, ongoing for eons, reflects the fundamental order imposed by gravity on the universe at its grandest scales. As observations continue and simulations improve, the clarity of this cosmic choreography increases. The pathways of galaxies, the accumulation of mass in clusters, the heating and motion of intra-cluster gas and the subtle acceleration across voids are recorded, measured, and understood within the framework of a single unifying gravitational influence. The Great Attractor, hidden from direct view, is revealed through its effects, its presence discerned by the motion it induces, guiding galaxies along a convergent path that defines the architecture of Laniakea. It serves as a reminder that even in the vast silence of space, unseen forces govern the unfolding of structure on scales beyond immediate perception. In the quiet vastness of the cosmos, the story of the Great Attractor is one of persistent, silent influence. Galaxies flow inexorably toward a hidden gravitational center, their motions tracing the invisible framework of the supercluster. The local group, with the Milky Way at its heart, participates in this continuous drift, moving as part of a larger, interconnected system that unites matter across hundreds of millions of light years. Observational precision, computational modeling, and careful analysis reveal the pathways of these motions, illustrating the remarkable capacity of gravity to shape structure and orchestrate the motion of the universe over incomprehensible distances and timescales. The flow continues, unceasing, a quiet testament to the hidden forces that govern the cosmos, a subtle reminder of the intricate order underlying the apparent vastness and emptiness of space.